Hello, I'm Mr. Craig, and today I want to talk about writing ionic compounds with Roman numerals. So let's go ahead and get started. Now, when we talk about Roman numerals, it's probably a pretty good idea to actually refresh our memory on what Roman numerals were. And I know that some of my students have mentioned to me that they're not sure what Roman numerals are because they've never been taught that, which is pretty interesting. But for writing chemical names that have a metal with more than one charge, you have to represent the charge with the Roman numeral. So it's nice to know the Roman numerals up to, and we won't go any higher than 7 or 8. So let me write those out, and make sure that you write these down if you need to at the top of the page, or just remember them in general. So here we go. Roman numeral 1, if I have the value 1, then it's simply an I. Roman numeral 2 is double I. If you're looking at Roman numeral 3, then it's 3 I's. Now here's where it gets interesting. Once we look at Roman numeral 4, then we start to use V's. So 4, and it's an IV, so whenever you put the 1 in front of the V, that means it's 1 less than. So then 5 is a V, and 6 is VI. So again, in the order, so it's 1 minus 5, 5, and then 6, and then 7, and lastly 8, which we will not go above 8. But these definitely are the big hitters right here, the ones that are on this side. Every once in a while, I may venture over to the Roman numeral 6 and 7, and if I get daring, I might go to 8, but we won't go above 8. So make sure you know this. If you're not sure, make some flashcards, review these, and memorize them. Okay? All right. Now, primarily the reason why we're using Roman numerals, and again, it's not my convention or my system. It's just the way that chemistry's been doing that for a while, and it's kind of historic more than anything else. But when we look at the metals in the middle of the periodic table, you'll notice that some of them do have one charge, like for example zinc and silver, which we've already been using so far. But the majority of these metals and transition metals have more than one oxidation number, or more than one potential charge. So when you say that, for example, if you're looking at copper, Cu, you can't just say that rust, which is iron oxide, or I'm sorry, if we're looking at iron, let's look at iron, sorry. If you're looking at rust, you can't say that rust is iron oxide. You have to identify what that ion is, whether it's iron 2 oxide or iron 3 oxide. Now when you hear me say the number 2 or 3, I'm actually telling you what the charge is. So when you write this out, that's when you use a Roman numeral. The reason why we use Roman numerals is so that we don't mix up and think that that's a big subscript or something. The Roman numeral tells us the charge on each, and I repeat, on each metal atom. So if you have, say, 2 iron atoms in your compound, then each of those is going to have either a +2 or a +3 charge for a total charge. So when you watch me work these out, keep in mind that the Roman numeral tells me the charge of each metal. Now, what we don't do for the nonmetals is, even though some of these nonmetals have more than one charge, we do not use Roman numerals. At least in honors chemistry, we do not use Roman numerals to represent the charges for these nonmetals. We're still going to go with the convention that that's a -3, that's a -2, and that's a -1. So whenever you see one of these elements all by themselves, don't say, ooh, which one do I use? It's always going to be the most common charge. Also, we've already spoke about polyatomic ions. Make sure you still know the name, the formula, and the charge for the polyatomic. So we're actually adding more and more pieces to this whole pie here. So keep that in mind. That's what we talked about on the first day. Second day is what we talked about with polyatomics, and today we're actually discussing the metals that have more than one charge. And it primarily deals with the metals that are in the transition metal area. There are a couple over here, like that's outside of that: lead, bismuth, and tin. These 3 are not a transition metal, but they do have more than one charge. So always always look at your periodic table when you're writing the name, because from this point on, if you look at a metal and they won't always be in this location that have more than one charge, and some of the metals in this location only have one charge, so we don't use a Roman numeral. Like for silver, you don't use a Roman numeral to represent the charge, because we know silver only has a +1 charge. So don't get crazy and just start throwing Roman numerals around. For like group 2A, you don't put Roman numerals for those because they only have one charge. Roman numerals are for the metals that have more than one potential charge. All right, so let's go to the homework here. Okay, and let me blow that up a little bit for you. Okay, so what we're doing again is you're starting off with the name and you're going to write out the formula. Again, my suggestion, I highly recommend this. Always write the charges above before you even start to write any of the formulas. Okay, so like in this, well, take that back. Write your charges before you write the subscripts. That's probably a better way to state that. All right, so looking at number 1, we have 10, Roman numeral 4. What that means is each 10 atom has a +4 charge. That's what that Roman numeral is telling us. 10, each 10 atom. Doesn't mean we just have one. We might have just one, but each one that's in this compound has a +4 charge. Chloride, again, if you look at your periodic table, hopefully you have that pretty well memorized, that since it's a group 7A, then it's going to have a -1 charge. So primarily I'm not going to go back to the periodic table for those, since you should be a lot more familiar with those. So the chloride has a -1 charge. Does that equal 0? Okay, the answer is absolutely not. So that means that we need 4 of those. So when I go and write this out, we have to write the correct symbol. So 10, SN, and then chloride, Cl. And since we have a 4 there and a 1 there, we're not going to put a subscript here, but we'll put our subscript there. So looking at that, this is probably a little easier because there is no Roman numeral in the formula. You never, ever place a Roman numeral in here. Only Roman numerals go in the name. Okay? Only Arabic numbers go as subscripts. All right, so let's look at number 3 here. We'll do the odds in this video. So number 3, we have mercury 2 acetate. Okay? So again, the Roman numeral tells us the charge on each mercury atom, which means that it has a +2 charge. Acetate is one of your 10 polyatomics. How do you know? Because it ends in ATE, and you have your polyatomics memorized. So keep memorizing those if you don't know them yet, or keep learning them, I should say. Acetate has a -1 charge, so when we look at that, we notice, actually let's scoot that over a little. So since acetate has a -1 charge, +2 - 1, that means I need 2 acetates. So now that I have it balanced, looks like I'm going to have 1 mercury. So again, mercury, one of your 52 elements, Hg. Since I only have 1 of those, no subscript. My acetate, which is C2H3O2, but since I have a 2 there, put the whole thing in parentheses. Remember, if you need to represent more than 1 poly, you've got to use parentheses. So in this case here, we have 1 mercury, 2 acetates. Therefore, each mercury must have a +2 charge. That's why we have a Roman numeral, because when we look at the table, it has an option of either a charge of 2 or 1. In this case, we're using the +2 charge. All right, let's look at number 5. Number 5 is copper 2 sulfate. Again, the Roman numeral means that we have a +2 charge on each copper. And sulfate has, very good, a -2 charge. So that works out quite nicely. So when we look at this, copper, and we have 1 of those, sulfate, we also have 1 of those. So in this case here, even though it's a 1-to-1 ratio, keeping in mind the charges, -2 + 2, and since copper can either be a +1 or a +2 charge, we have to use the Roman numeral to tell everybody which charge we're using. Okay, so CuSO4 is copper 2 sulfate. All right, number 7, bismuth, Roman numeral 5, carbonate. So here we have the Roman numeral 5, which means that bismuth has a +5 charge on each bismuth atom. Carbonate, again, it's a polyatomic, so that means that we have a -2 charge. Does that equal 0? Not even close. So here we get to have a little bit of fun, okay? So here's what you get to do. Look at this and ask yourself, how can we get these values to equal 0? Well, you could do 2 and 5. Not a bad idea. That'll give you a value of 10, plus 10 minus 10. So that when we write this out, we have bismuth, and then I'm going to put a 2 here. 2, and then carbonate is CO3, but we need 5 of those, and then put it outside the parentheses. Make sure and double check, can these be reduced down any further? The answer is no. So we have Bi2, parentheses CO3, parentheses 5. Why? Because we had to balance out the charges in this case. Okay. Looks like we're going to the top. So let's look at number, what is that, number 9? Number 9. Nickel 2 phosphate. Okay, nickel, if you look on the periodic table, you'll find that nickel can either be a +2 or a +3 charge. Don't have to memorize that, you just have to be able to look at the periodic table and see that. So in that case here, we know that it has a +2 charge. And phosphate, again, ends in ATE, and phosphate, PO4, with a -3 charge. And no, that does not equal 0. Let me scoot that over a little. Okay, so that means that we need to do some multiplying to actually both of these. So that's going to be multiplied by 2. That is going to be multiplied by 3. So nickel with 3 of those, phosphate 2 of those. So when we write the formula, nickel, and then put the 3 there, and phosphate, PO4, parentheses 2. Okay, so again, nickel, Roman numeral 2 phosphate, looks like that. Okay, hopefully this is getting a little easier. Go ahead and pause the video and try the next couple on your own, and then take a peek at it. All right, manganese 4 oxide. So manganese has a +4 charge in this case, and if you look at manganese, manganese is one of the elements that has a couple, so it actually has 4 of them. It can be a 7, a 4, a 3, or 2. Don't have to memorize it, just have to look at the periodic table and see that. And in this case, it does have a +4 charge. The oxide has a -2 charge, so when we look at that, we're going to go, okay. So we have +4 -2, and again, multiply that out. So we get a 2 there. Okay. Now, remember when I talked about switching charges? That's okay, but if you do that, do realize that 2 and 4 can go into each other. So that when we write this out, really, we only have one manganese. Okay, so if you have manganese, Mn, and then the oxygen, or oxide, 2. So if you wrote it out, not like that, but initially you put a 4, I'm sorry, not a 4 there, sorry, check that. If you put a 4 here and a 2 there, you're thinking in the right plane there, but we can't have those because we need to have the smallest whole number value. So this is what's nice. We have a 1 there and a 2 there. So manganese 4 oxide looks like that. Okay. Number 13, chromium 4 carbonate. So again, or I'm sorry, that's a 6, my bad. So the numbers after, so we have a 6 there, and carbonate is a -2. So same thing, if you're planning on switching those values, make sure that you actually can ask yourself, will they be reduced? And in this case, we would, because this will equal 0. Actually, let me scoot that over a little bit. So -2 there, and a 3 there, so that all equals 0. So when we write this out, we have chromium, and it has a +6 charge, but we only need 1 of them. And then carbonate, it's like that, but we're going to have 3 of those. And so again, if you do the crossing and put a 6 down there and a 3 there, 3 and 6 can be reduced down to 1 and 3. Again, some of you are like, what is he talking? Don't worry about it. Just keep doing the balancing of charges if that's not what you want to do there. All right, number 15. Here we have lead 2 iodate. So the Roman numeral 2, 2 there. Iodate is a -1. That does not equal 0. So that means that we're going to need 2 of these iodates. And when you look at lead, lead's over here. Okay, lead can either be a +4 or a +2 charge. Again, you don't have to memorize that because you'll have your periodic table in front of you. So lead, which is Pb, and the iodate, which is IO3, and since we need 2 of those, there's your lead 2 iodate. All right, so let's take flip the page over here, and now we're going to work in the opposite direction. So now we really need to look at our periodic table, okay? Here's how we're going to attack these. We have our metal with more than one charge. We have our non-metal. For the non-metal, again, keep in mind, we are not using multiple charges for these non-metals. So you probably, actually not probably, you will use the non-metal to help you tell what the charge on the metal is. Use the non-metal charge to help you tell what the charge on the metal is. Okay? So when looking at this, we know that we have how many oxygens here? That's right, we have 1 of those. So we have, whoops, there's a red color there. So since we have 1 oxygen, we have 1 oxygen with a total charge of -2, how many 10s do we have, or 10 atoms do we have? We have 1. So what must the charge on this 10 atom be for it to equal 0? It has to have a +2 charge. How do you know? Or, how do you know it's right? You go back to your periodic table, you find 10, and you ask yourself, does 10 have a +2 charge? The answer is yes, it can be either 4 or 2. Now, since you know that it has 2 charges, you have to tell everybody that you're using the +2 charge. So when you go and write this out, you can't just write 10 oxide, you have to write 10. The charge, in this case, is +2 because it has either a 2 or 4 charge. Now, if it only has 1 charge, there's no need to show a Roman numeral, but this does. So 10 Roman numeral 2, and it's oxide. Okay? So the Roman numeral tells me the charge on each 10 atom. Well, we only happen to have 1, so that just so happens to be the charge for that. All right, looking at the next one, we have FeS. Again, let the charge of the non-metal tell you what the charge on the metal is. So again, when looking at sulfur, where are you? Oh, looks like I'm too high on there. So sulfur has a -2 charge, so we're going to go with that charge. We're not looking at these other charges, not yet, not for a while yet. So we're going to use the -2 charge. So when looking at that, you know that sulfur has a -2 charge, and you know you only have 1 of them. It has to equal 0. How many iron atoms do you have? 1. What must the charge on the iron be? Very good, a +2 charge. So go and check, make sure that you did your math right by checking to see that you have the correct charge. When we look at iron, iron can either be a +2 or a +3 charge. Okay, so it can be either 2 or 3, so that means we have to use a Roman numeral. So in this case, it does have a +2 charge, so you'll say iron, Roman numeral 2, and it's sulfide. Again, the IDE means that you're looking at a single element, or a single non-metal. Okay. All right. All right, number 5, we have lead carbonate. Okay, well that's pretty easy. Carbonate only has a -2 charge, so we don't have to worry about digging around trying to find that. So carbonate's -2, you have 2 of those. Lead, now we have to look for lead. Lead can either be, do I have it far enough over? I don't think so. Bring it over a little more. So lead can either be a +4 or +2 charge. And in this case, we're going to, how many lead atoms do we have? Very good, we have 1. Therefore, the charge on this lead, if we have -2 times 2, and we only have 1, what must the charge on the lead be? Very good, +4. So, again, I found that out because I have 1 lead. There is no subscript, but there is, it's a 1. -2 times 2, so it has to be a +4. Let the algebraic sum equal 0. So lead can either be a 2 or a 4 charge. We're going to use the 4 charge right now. Okay, so when writing this out, you have your lead, Roman numeral 4, and if you want to leave it like that and not put the things on there, that's fine, and it's carbonate. Lead 4 carbonate. Now again, we only have 1 lead atom, but we'll later get into some examples where we have multiples. The charge on each lead. Okay. Number 7, we have chlorine. Again, that's in group 7A, so it has a -1 charge. There's 2 of those. Let your non-metal tell you what the charge on your metal is. We have 1 iron atom. Iron can either be a +2 or a +3 charge. How do you know? You look on the periodic table, find iron, it could be either 2 or 3. So in this case, it has to be a +2 charge because the total charge on the non-metals is a -2. So we have iron, Roman numeral 2, and this is chloride. All right, let's look at number 9. Number 9, we know our polyatomic, iodate, which has a -1 charge. And we have 3 of those. How many cobalts do we have? Just 1. So therefore, the charge on the cobalt must be +3. When looking at your cobalt, cobalt can either be a 2 or a 3. So that fits into our bill of a +3. So we write it out as cobalt, Roman numeral 3, and that's iodate. Cobalt, Roman numeral 3, iodate. Well, I sure hope I put some metals with more than 1 on there. This is making me a little nervous. If not, I think I'm going to change this midstream. Oh, good, I do. I have a couple on there. Okay. All right, so let's look at number 11. And I think I'm going to do 13 and 14 because I noticed that there's more than 1 there. All right, here we have an interesting one. Okay. No parentheses. We have Hg, C2, H3, O2. Again, if you're not sure, identify your metal. Whatever's left is your non-metal. Remember that trick? That's a good one to remember. All right, so we know the charge on this compound, or on this polyatomic, C2H3O2, as a -1 charge. That's acetate. If there's only 1 of those, and we have 1 mercury, then the mercury must have a +1 charge. So looking at mercury, it can either be a 2 or a 1. So the +1 charge, so our +1 charge is a good one. So we use that. So here we have mercury, Roman numeral 1, and we have to show the Roman numeral 1 even if it has a +1 charge. Again, doesn't matter what the charge is, as long as it has more than 1 charge, you have to tell me what that charge is. And then acetate. Okay? All right, let's look at number 13. I'm going to do 13 and 14 since these metals have more than 1 charge, and I'll skip 15. Okay? All right, so finally, we're getting to a good one here. Phosphate is one of your polyatomics, and it has a -3 charge. We have 2 of those. Okay? Ask yourself, how many iron atoms do you have? You have 3 of those. So to balance the charges out on this, we have a -6 charge over here. We have 3 atoms, so we're looking for a total of a +6 charge on the right-hand or left-hand side. So that means that the iron has to have a +3 charge. checking the charges for iron. Iron again can either be a 2 or a 3 charge. So what that means is it has a +2 charge. So when we write this out, we're going to go iron, Roman numeral 2. Okay? Remember, the Roman numeral tells us the charge on each metal atom, not all the metal atoms, each. So it's iron, Roman numeral 2, phosphate. Okay? That's really important because if you go from the name to writing out this formula, and again, let's just cover that up just for a second. Okay? So you don't see that. I know you have it on your paper, but when writing this out, if you say, okay, I have iron with a +2 charge, okay, and I have phosphate, which is PO4, and it has a -3 charge. Does that equal 0? Absolutely not. So what that means is I need 3 of those and 2 of those. So I'm going to put that in parentheses with a 2, and then I put a 3 there. Does that give us our formula here? Absolutely. So again, the charge tells us, or the Roman numeral tells us the charge on each of these iron atoms. So that's why you have to indicate what the charge is. It's not the total charge. Because if you said that that was a 6, then that would mean I'd have a totally different setup here, where I'd have 1 iron and I'd have 2 of those, and that would not be the same thing. Okay? So remember your rules for the Roman numerals. All right, let's do the next one, number 14, since it's another multiple. Okay? So looking at the non-metal first, phosphate has a -3 charge. We have 2 of those. How many Mns or manganese do we have? We have 3 of those. Therefore, the charge on each manganese must be a +2 charge. Check your periodic table. Manganese can either be a 7, a 4, a 3, or a 2. There it is. There's our +2 charge. So when we look at this, we're going to call this manganese. So manganese. And again, Roman numeral 2 and phosphate. Manganese, Roman numeral 2, because of each manganese atom has a +2 charge. All right, I'm going to skip 15 since you already did that. And let's look at the last one, 17. So again, look at your non-metal, which has a -1 charge, and there's 2 of those. How many irons do we have? 1. So therefore the iron must have a +2 charge. And if you look at iron, it can either be a 2 or a 3. So that's legal. So when we go and write this out, it is iron, Roman numeral 2, hydroxide. All right. So again, when working these types of problems out, it is imperative to have your periodic table out, because from this point on, if your metal that you're writing has more than 1 oxidation number or more than 1 potential charge, you have to tell your audience or your grader what the charge is. Okay? You can't just call this iron hydroxide. Okay? Iron hydroxide doesn't tell us what the actual formula would be, because iron can have either a 2 or a 3 charge. And if we look at tungsten, okay, if I blow that up and look at tungsten, where'd tungsten go? It's over here. So if I look at tungsten, tungsten can either be a 6, a 5, a 4, a 3, or a 2 charge. So you can't just call something tungsten oxide. You have to tell what the charge on each tungsten atom is, if that were asked. And it will be. So I hope that this has helped out a little bit.